So let's keep going. We want to continue our discussion of the path integral that generates string scattering amplitudes, and in particular the ghost sector. So let's look at S ghost, the ghost action that we derived in the last class. And this action was took the form BPC, where this was that fancy inner product, I mean the obvious inner product on traceless two tensors. And P was the operator. P mapped, things with one index to things with two indices. Okay, I wouldn't try to be fancy. PC mu nu is equal to del mu C nu minus plus del mu C nu minus del dot C G mu. Thank you. Okay. Now, you see, we were working on a general metric G mu. Okay? But, yeah, okay, for the next 2 or 3 lectures, we're going to examine all the structures that entered into our formula for this scattering amplitude and check that the scattering amplitude makes sense. What we mean by makes sense, we will explicate as we go on. One of the things that we must mean, however, is, if you remember, we had the string path integral based on an auxiliary metric. Do you remember we had a gauge fixing, we had these foliations, and we chose a particular slicing, some G0 of mu nu on each slice, some particular candidate metric. Okay? And if we've done everything correctly, it had better be true that the final answer does not depend on what our choice of G0 was. Namely, if we take G0 and move somewhere else on this space, it had better be true that we get the same answer. Now, moving somewhere on this foliation space, you move by 2 operations: diffeomorphisms and Weyl transformations. Diffeomorphisms, okay, it's clear you'll get the same answer. That's just diffeomorphism. The Weyl transformations are more delicate. Okay? So it had better be true that G0 and G0 mu nu times e to the power 2 phi generate the same path integral for string theory. Is this clear? Okay? So the action that we wrote down, both for the matter sector as well as the ghost sector, had some G0 in it, a metric on the Weyl sheet of the string. Okay? And it had better be true that the final answer does not depend on exactly what your G0 is. Okay? So this is one thing that we will move towards checking. We will try to do that this lecture. Okay? The various other things we have to check. For instance, we chose in vertex operators.
You're saying this should be saying for G0 and G0 omega.
Yes.
All
omegas, but the diffeomorphisms will be trivial. So the thing that really needs to be checked is the Weyl transformations. Okay? Another thing that we will need to check is that when we wrote down our formula for scattering amplitudes, we chose to fix some vertex operators at fixed positions, and we left other vertex operators unfixed. So there are 2 things to check. First, the answer should not depend on where we chose to fix the vertex operators. Second, the answer should not depend on which vertex operators we chose to fix. Okay? And as we go along, we will see other things that we need to check. So there are many things that need to be checked in order to see that this formula makes sense. And we're going to start checking many of these things today, and we'll understand it better as we check them. Okay? But to start with, what I want to say is the following. Look, we're going to, by the end of this lecture, check that G0 and G0 times e to the power 2 phi give you the same answer. Okay. So now, we've got this metric. Let me assume for a moment that it's true. So we've got this metric with a g naught times e to the power 2 phi. We've got this metric which is some g naught, and g and g times e to the power 2 phi are going to give the same answer. Okay, now up to the freedom of doing diffeomorphisms and wild transformations in an open neighborhood, it is certainly true that every metric can be brought to the form dz dz bar. Okay, so more precisely, by diffeomorphisms in an open neighborhood, you can always bring a metric to the form some e to the power 2 phi dz dz bar. Okay, one way of thinking of these moduli, the many different ways, the many different inequivalent things, the ones you can't get to, is as follows. You know, over the whole manifold, you may need to take that manifold and patch it together with many patches. In each patch, you bring the metric to this form. Okay, but there's a coordinate transformation that goes between the transition functions that goes between the first patch and the second patch. Now, if the transition functions are such that z's are functions of z's, okay, then you know, on this overlap, what you get is just a change in the phi. Yes. And that doesn't matter. But you see, the moduli from this point of view are going to be the statement that in one way of doing it, z is a let's say you choose your definition of z such that, you know, with some standard metric, z's here are functions of z's here. To get to the next manifold, you'll need to make the z's here functions of z's and z bars there. Okay, and this is one way we will have of exploring the space of moduli. This I will go through in detail perhaps at the end of this lecture, tomorrow's lecture. But I said this all just to motivate the statement that if we're interested in this, in looking at this theory locally, patch by patch, we can always think of this thing on the metric e to the power 2 phi dz dz bar. Everything interesting about the metric then goes into transition functions between patches. Okay? I will explain this in detail either this class or next class. We'll encounter these things one second called Beltrami differentials, which will allow us to characterize the differences in ways of patching together. We'll understand this in detail, but not immediately. Yes, please.
What do you mean by moduli space?
Moduli space is the number of inequivalent, the p parameters. You remember the number of metrics that we couldn't get to, the number of parameters that we needed to add in addition to diffeomorphisms and wild transformations to cover the space of all metrics. Yes. I'm going to explain the statement very soon in detail. Right now, I just want you to take on faith, or it's plausible, I think, that locally we need to deal only with metrics of this form, e to the power 2 phi dz dz bar, and then by patching together so this, we can build all kinds of metrics. Okay, so for the next few minutes, we're going to study this action here in a metric of this form. Okay, and I want to study this action really explicitly.
The transition functions are going to be some pure gauge, right?
No, you see, the differences in transition functions give you different manifolds. You change transition functions.
Right. This is manifold.
Yes. Okay. Okay. So let's take this action and evaluate it just, you know, explicitly. Okay, in this sketch. So what do I mean? So what is this action? The action is square root g b mu nu del mu c mu plus del mu c mu plus minus del dot c in a G medium. Now I'm just going to evaluate every term here just completely explicitly for a metric of this form. Is this clear? Okay, so let's do it. Okay, so this metric we can write as e to the power 2 phi times eta mu nu. And for such metrics, or delta mu nu, Euclidean, Okay? And for such metrics, let's evaluate everything. So one of the things I'm going to do is to evaluate the Christoffel symbols. Okay? So let's remember, in order to evaluate the Christoffel symbol eta mu alpha beta, what we need to do is to raise g mu nu by half, by 2, and then this thing comes with a nu, so it's g nu alpha beta plus g nu beta alpha minus g alpha beta nu. That's the formula for the Christoffel symbol. Okay? Now in this particular case, everything's very easy. So this thing is e to the power minus 2 phi delta mu nu by 2. And then we get each of these is proportional to e to the power 2 phi times the derivative of phi. So the e to the power minus 2 phi and the e to the 2 phi will cancel. Okay, so I'm getting rid of that. And then what do we get? We get del beta phi plus del beta 2 phi. So let's cancel the 2. Thank you. Del beta phi plus del alpha phi minus del nu phi.
No, but there will be indices all over the one will be delta nu alpha.
Absolutely, absolutely. So this is delta nu alpha, this is delta nu beta, and this is delta alpha beta. Absolutely right. Okay. So we can. So this is equal to delta mu nu. It's mu alpha.
Yes.
Del beta phi plus delta mu beta del alpha phi minus delta alpha beta del nu phi. Del mu phi. Okay, where Euclideans up and down are all the same. Okay, so there's no significance to the up and down. I'm not trying to be careful about it. Okay? Great. So now the next thing we're going to do is to evaluate the covariant derivatives that we have in that expression. So we have the covariant derivative del mu c nu. So this is equal to del mu c nu. Okay. Now plus, because it's an upper index, sorry. It makes no, yeah, anyway. Yeah, sorry. Let me, I've put it all up, right? So let me. Okay, so it's del mu c nu plus, let's
Put the metric
yeah, you want me to put a mu here? Fine, we'll do it. Okay, plus gamma mu theta nu c theta. Right? Okay, so that's equal to del mu c nu plus, and now I'm going to use this this formula. So this gave us delta nu mu del theta phi plus delta nu theta del mu phi plus delta
minus delta lower alpha beta,
mu,
lower mu.
mu theta, all up
Yeah,
down, all this.
up, yeah.
Okay. Yeah. Del nu phi c theta. There's no significance up and down. Okay. C theta.
That's good.
Yeah, yeah. Okay? And now what we get, now I have to evaluate this expression here. This expression for that object. Okay, so let's do it. Well, yeah, it's a pain, but let's do it. This is del mu c mu plus del mu c mu plus minus del dot del dot c has one lower, one contraction.
No, we could use this 1 over root g diagonal.
We could. Okay, yeah. I'm just saying that this part. Okay, fine. Maybe we should do that. Let's do this part first. Del mu c nu plus del mu c nu. Okay, excellent. So now, of course, we've got these terms. That's from here. But now we want to get the analog terms from here. So what we want to do is to symmetrize in mu and nu.
Yes.
Do you see that these terms cancel each other in
Yes.
that process? Okay, they're exactly the same, except that they're antisymmetric. Okay, so if we symmetrize, we get, but this term, of course, is by itself symmetric. So you get plus 2, okay, now this times c theta, so delta mu nu times del phi, del theta phi c theta.
But in this case, one index has been raised, the derivative index. So there will be a factor from the metric, right? To the minus, right?
Well, what are we saying? Sorry.
No, we have raised the index mu.
You're saying this is here.
Yeah. I mean, there should be some overall.
You're right. You're right. You're right. So this I evaluated with del down.
Yes.
Okay, and then if I evaluate with del up, I'll get an e to the power minus 2 phi of this. Okay, so del mu c nu plus del mu c mu is equal to e to the power minus 2 phi times this object. Is this clear? Great. Okay, now let's use your advice and evaluate the next term using this fancy formula. So the last term that we wanted was del dot c times g mu nu. G mu nu is, so that's minus del dot c times e to the power minus 2 phi times eta mu nu. Now what's del dot c? The constraint, no, this is what's making the whole thing traceless. We put that there because the trace of B was there. Okay? So now let's go. This del dot c, by Upmanyu's advice, is 1 by square root g.
Yeah.
But square root g is e to the power 2 phi.
E to the 5. No, it was
E to the power 2.
Yeah, right.
D mu e to the power 2 phi, and then c mu. Okay? And so now this whole thing, so that's this times e to the power minus 2 phi times eta mu nu. That's what this term is. Okay? And when we evaluate this, what do we get? When we evaluate this, we get that it is, so there's a term where the del mu hits the 2 phi and a term where the del mu hits the c mu. So the term where the del mu hits the c mu is e to the power minus 2 phi times d mu c mu. Right, that's the term where, because this and this cancel, there's e to the power minus 2 phi times eta mu nu. And then the extra term, that's what's interesting, is plus 2 del mu phi times e to the power minus 2 phi times eta mu nu. Times c mu, yes. Del mu, sorry, so del alpha phi c alpha. Now we've got to take this minus this. Right? We wanted to take this minus this. And the whole point of this exercise was to show you that this and this cancel. Everything is delta, I'm sorry. You see 2 delta mu nu del phi dot c. Cancels the 2 delta mu nu del phi dot c. Is this clear? And therefore this whole quantity here evaluates to what? That whole quantity there evaluates to e to the power minus 2 phi into what it would naively be. That is d mu c mu plus d mu c mu minus d mu c mu d alpha c alpha delta mu. When now every derivative is in flat space. Is this clear? Okay? So if we take this and plug this into the action, what do we get? We get e to the power 2 phi, that's from square root g, times e to the power minus 2 phi, that's from this term, times integral, but that cancels, so there's an integral overall outside, but these two cancel with each other, times b mu nu into this object, d mu c mu plus d mu c mu plus delta mu nu minus del dot c. Yeah, exactly. But go on. But when the basic fields of the theory are chosen to be C upper and B lower. I have been very careful to write it in terms of C upper and B lower. If you did the same exercise with C lower, you know, that's related to C upper with some factors of e to the power phi, and some derivatives of phi would be left over. This you can try as an exercise. So what I'm saying is that this action here, as Indranil said, is classically while invariant. Yes, exactly. That it's classically while invariant, okay, when expressed in terms of C upper and B lower. It's just the while transformation of this flat space action.
Otherwise, there would have been no cancellation
with the phis. It does just won't work. Yes. So now when we go, now we are experts, right? We all know that while invariance means conformal invariance if we're not going to change metrics. But when we have a conformal field theory, we have to know how fields transform. Because these objects did not transform. These objects did not transform under while transformation. They transform under conformal transformations only by diffeomorphisms. And therefore we conclude that, okay, we also know B is traceless. Traceless means now we go to ZZ bar coordinates. Traceless means the components of B are BZZ and BZ bar Z bar. The components of C are CZ and CZ bar. Under diffeomorphisms, this guy has weight -1, 0, and this guy has weight 0, -1. It's upper index. Under diffeomorphisms, this guy has weight 2, 0, and this guy has weight 0, 2. So you see what we're going to get is a conformal field theory, but with fields of weights 2, 0 and 0, 2, -1, 0 and 0, -1. Our fields in the problem, the C's, C bar, B and B bar, are going to transform under conformal transformations with these assignments. Is this clear?
And by the standard arguments, this will also be purely holomorphic or anti-holomorphic?
Yes, we'll see that very soon. Okay? But it's very important to know that logic, just physics, gives us the weights of the conformal. Because this is the action, we knew the action in full curve space. From it we could deduce if it is wild invariant, and if it's wild invariant, in what way. What? This field has negative conformal dimensions, yes. And we said that there's something wrong about that. So there's going to be something wrong about this theory. Yes. 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 Exactly. If you write, no, B lower C upper. They don't.
You do whatever you do, and then you need to say how it transforms.
Exactly. If you wrote it in terms of B upper,
yes,
we could do that, but then it would have transform under wild transformations.
That's all. Like
That's all. So then it would have transformations under both diffeomorphisms as well as wild transformations, and once again you'd conclude this.
that makes sense, right?
Yes.
I mean, otherwise it's like partiality kind of thing.
No, of course.
Yeah. Okay.
Yes.
If I did the inner product of AB and instead did inner product of BA, like which would swap the uppers and lower indices, it wouldn't be that straightforward of a symmetry?
Why don't we just work this out? You see, this is the action written in, so let's just write out the action in the metric phi with e to the power 2 phi. Let's write, we've written out the action. The action is B mu nu d mu c nu plus d nu c mu minus del alpha c alpha eta mu nu. This is the action. It's just what it is. Right? Now, if you want to evaluate in terms of lower, let's do it. No, this is the action without the root chain. Right? Everything has been eaten up. Okay. Now let's just write it in terms of B lowers. So if you want to do it in terms of these B lowers, we will get what? We will write it as integral of B mu nu times e to the power 4 phi. Because B mu nu is just this. This is harmless because it's homogeneous. What's interesting is here. Here you get the derivatives acting on something with an e to the phi. Then you get d mu c nu times e to the power minus 2 phi plus blah blah plus. Okay? And then this quantity, now if you choose the c nu to transform with this weight, then it behaves good under wild transformations. It will compensate the wild scale. I mean, I'm just saying something trivial. I'm saying I've worked it out in the way where I don't have to say it complicatedly. Once I've worked it out this way, you can put it in any language you want. There's nothing interesting. What? There was another thing? Maybe. I'm sorry. Yeah. Okay.
So if I look at the form up there,
Yes.
right, then the covariant derivative was designed so I can pull the metric in and out of it, right?
The covariant derivative.
It's metric compatible. So that issue that you're pointing that you have.
No. But what we're trying to do is to write it in terms of metric eta.
Okay.
See, what have we done? We've taken this action here and written it. We want to see how this action depends on the field phi.
Yeah.
I'm saying that when we write it in terms of this thing, the action does not depend on the field phi. Of course, this is always right, but then if you express it in terms of a metric and perform a wild transformation, you won't get the same action unless you also do something to the fields. This is not a question of diffeomorphism invariance. It's a question of wild transformations. Is this clear? Okay. So we've concluded that this action is wild invariant provided we assign transformations. Yeah, this action in the end will be conformally invariant with these transformation properties for these fields. You could say it more complicatedly than I said it. You're free to do that. You'll get the same answer. That's what Eames and Neil wanted. Okay. No, I know. You just wanted to make sure it was all making sense.
And also, I think now I fully appreciate the point that you actually subtracted out the trace from here.
Exactly.
Otherwise,
It wouldn't have worked.
Yeah. But we could have worked with fewer, symbols, even if we had not subtracted out the trace. But the subtracting of the trace manifestly makes it wild invariant.
Yes, we don't. Yeah, exactly. That's why we deal with the operator in like this. Is this clear? Okay. So now that we're happy that we've got this, please go on. Which operators? Upper. Anything now is just this thing times an e to the power 2 phi. So this quantity c. Okay. The quantity in terms of which the action in flat space, in the conformal field theory, takes this form, just has this dimension. You can break up the dimension into the dimension of diffeomorphism minus while, or just have it as just dimension of diffeomorphism. But the final answer will always just be the same. Okay, the object that appears like this quantity has dimension minus 1. Is this clear? Good. So now that we are all happy.
These are the fundamental fields in our path integral that we are going to do.
Yeah, when we write the action this way, and we do the path integral with this, these must be assigned dimensions minus 1. These must be assigned dimension 2. Good. So now that we've understood this, now let's move to complex notation. Okay. In complex notation, what does this action become? The action becomes S ghost is equal to, and now I'll use the normalization that Polchinski likes. 1 by 2 pi maybe, but I'll just check what he likes. One by 2 pi d2z. What he means by d2z is not very clear. Okay. d2z, zz. Okay, it's clear that this thing is proportional to that. Right? Why is it clear? It's because B is traceless, so it has only ZZ or Z bar components. Okay, so this is bzz times del z bar cz bar. Right, as you said, when you evaluate in components, this part doesn't matter because it contracts with something. So it's just these, okay, because these are both z indices, should be both z bar indices down. So z bar, z up or z bar down. The last term doesn't contribute when you evaluate it because it's contracting against a traceless object. Okay, I'm going to call this. I don't know why Bulchinski's. Oh, maybe he wanted to make some point. I'm going to call this CZ bar. Oh wait, no. This is CZ because this is the holomorphic. Right. Let's do this. Yeah. These guys are going to. Okay, fine. So let's stick with this. Okay, and I think for Polchinski, d2z is equal to 2 dx1 dx2. If you wrote it in normal Cartesian measure. Okay, so fine. So this is the action we want to understand, and now we. What? Because I think he's taking just Jacobian. He's doing z as x. Yeah. No. Okay. So let's. So now we're going to spend like half an hour, 45 minutes, maybe a little more, understanding this theory. Okay, so that's our assignment now. We didn't ask for this, right? We started off trying to understand number go to action. Then we got this Polyakov action, which became conformal in terms of the matter. So we had to study that matter action. Fine. That was fair because we wanted to study embeddings. We didn't ask to study this theory, but we're forced to because gauge fixing, the measure for the path integral gave it to us. So we need to understand.
In electrodynamics, there are certain
Yeah, you're talking about those alpha gauges, right? No, please go on.
there are certain gauges in which you have ghost free kinetic term.
Yes.
Here is nothing like that.
Well, light cone gauge would be like that. So, as in electromagnetism, the price you pay in going to ghost-free gauges is giving up Lorentzian layers. Yeah.
You want theory, you can take the Lorentz gauge.
Right. There, the ghost is there, but it doesn't couple to anything, so it's trivial. Yeah. No, but in this case, we're actually interested in the partition function. So we're interested in things that are more sensitive than we're normally interested in quantum field theory. What? Partition functions are more sensitive because you see normal quantum field theory, when you're computing correlation functions, some quantity that comes overall outside that's independent of some insertion cancels. Here we're interested in more sensitive things than that. We're actually trying to compute this partition function. Okay? So even when things are quadratic, like they are with these ghosts, we need them. Because for instance, the dependence of the partition function on the Weil factor, we'll care about these cases. Okay? So we're doing slightly more sophisticated, with slightly more careful things than we normally do. Yes. No. I mean, what we're interested in is actually the path integral with those insertions. Now we may use tricks to calculate it, which involve first calculating the ratio and then fixing the normalization by some other method. But we really want the whole thing. We want more than a normal quantum field theory. And you will see how this is the kind of thing that we try never to evaluate in quantum field theory. Even for a harmonic oscillator to evaluate it is a pain. You do it by basically Maybe somebody does it carefully, but usually normal people will fix the normalization factor by comparing with Hamiltonian formulas. Okay, we're going to do similar things. We'll have a normalization floating around. We'll care about it, but we'll use various tricks to fix it. Okay, and then.
Why is it so important? I don't know the importance. Why do we?
Well, firstly, let us the thing that we started off trying to compute was this sum over all paths, which mapped to the path integral with this, not that divided by something.
Yes, but usually you want that if there is no such procedure, like nothing like this happens, this is a 0 point something is. I'm not, sorry, I'm not understanding the connection. Why not divide by 0 point something? Is there something going on there?
Yeah, it's, this quantity is going to be tied to things like the string coupling. This quantity. It's my request is, let's ask this question once we use it.
Okay.
When we actually compute string amplitudes, we will see where these normalizations go. And then we can address this question more clearly. Okay.
I think last class I asked you that you said it's without insertion this will be well-defined.
What?
So without insertion, without any insertion, this is well-defined.
Yes.
And that is what the normalization factor is.
No, but I mean, when I'm interested, let's say I've got some insertions.
Yeah.
I want, you're saying that, okay, that's another good answer. You can't even divide by the normalization.
I know. So
Yeah.
that's why I am trying to.
Yeah.
What is going on?
Yeah. Hang on to see how we use it. Yeah, it's related to a question you came and asked me. Right, as you said, for the sphere it would make sense. Yeah. Okay, good point. Okay, so for now let's turn to a relatively simple question, namely to understanding the quantum field theory of this action. Okay, so we're going to do all the games that we played with the X action, we'll play with this game, or with this fellow. So the first thing I want to do is to compute the 2-point function. The first thing I want to do is to compute the 2-point function of this theory. So let us say that our path integral e to the power minus s cost, is defined by integral dB dc e to the power minus s cost. Okay. Now we're going to do the kind of thing we did before. That is, we're going to do the following.
This is just over the non-zero mode, right?
What? The full path integral without, no, with everything. Yeah. It's a good question. Just a minute. Because I'm going to do formal manipulations and you'll tell me there's 0. Let's just. You see, at the moment what I'm going to do is to work on this theory just on the plane. Okay, I'm going to work on the theory on R2. Now, the question of zero modes will come about when I take patches of this and sew them together. This theory, as defined in R2, will have no zero modes, right? Give me a minute. You see, every field, every killing, it will blow up either infinity or at zero. See, the thing that allowed it was the conformal transformation that turned infinity tame for SL2R. Do you remember how we, see, what we had was, let's say we were doing analytic coordinate changes. Okay, so we had z going to z plus delta z. And then we Lorentz expanded this. Okay, this delta z was equal to an z to the power n, let's say. Now clearly, if we just work in the coordinate z, something like this either blows up at infinity or at zero, other than the constant which is okay. However, what we did was to say, when we were working on the sphere, our rule was that the sphere was two patches. Okay. We had the sphere, and we did a stereographic projection for the first patch, stereographic projection for the other patch. The relationship between them was z goes to 1 by z. And so to judge what happens at infinity here, we didn't use the first patch. We used the second patch. So we did that z goes to 1 by z coordinate change. And that tamed some of these guys that looked like they were blowing up, actually didn't blow up. Those were the SL2Rs.
So blowing up at a region on this, blowing up at some region on the sphere sounds significantly more problematic than blowing up at infinity on the planet.
What?
Just naively.
Yeah.
Blowing up at an actual point on the sphere is significantly more problematic than blowing up.
Yeah, that's good. So I have to define my boundary conditions when I do this path integral for you. So when I say the plane, this is not well defined unless I tell you with what boundary conditions. Okay? And my boundary conditions are going to be C and B go to 0 at infinity. So for the formal manipulations of the next 20 minutes, I'm going to work with the theory on the plane defined with these boundary conditions.
But then these can't be holomorphic or anti-holomorphic, because then they have to be zero everywhere.
Well, yeah, they can't be holomorphic or anti-holomorphic unless there are sources. Exactly. So it's like del square phi equals 0.
Right, so,
In Euclidean space, has no solutions where phi vanishes at infinity. We normally study the theory phi vanishing at infinity. Here we get a non-trivial field theory because we allow sources. Okay, that's what we're going to do. So for these manipulations, I'm working on the plane with these boundary conditions. I will use this structure, what I derive, I will use only locally and then stitch together to also deal with situations which are more. So it's the same philosophy, right? We're taking a patch, okay, and we're studying the theory of the patch with a particular boundary condition.
So in some sense, the way we're going to think about these vector fields C or we're also going to think of them defined locally and hope we can patch them together.
We will eventually, that's always, because always our manifolds are patches of, made up of things of patches. So in any given patch you can use some z bar coordinate, but then you have to patch. Even for the sphere, that's how it is, right? As we'll see.
Right, and there's the implicit assumption this is the kind of object that could be globally defined on the sphere. Or, right?
What do you mean, this is the kind of object?
No, well, you can't, there's not everything can be globally defined on the sphere. Or like we had last time, right? We had, or we mentioned that say for higher genus objects you can't find any sort of well-defined global transformation. Right? So I'm just saying that
we're going to do a path integral. And the path integral we will do patch by patch and then match together patches. Right? So, what a C insertion here is maps to a C insertion here by a certain rule, by a patching rule. Okay, we'll see how this works in practice. Okay, right now we're dealing with a simple theory. Just on the plane, with boundary conditions, everything vanishes at infinity. This kills all 0 points. This precise statement of the boundary condition will kill all 0 points. Okay, good. So now what I want to do is some simple path integral manipulations with this theory. It's a good question. Okay, so the manipulation I'm going to do is the following. I'm going to say, consider BZZ, for instance. Okay, BZZ I'll call B. Okay, so now I'll lighten the notation by calling this guy C, and this guy B, and this guy B bar, and this guy C bar. Okay, so S ghost is equal to 1 by 2 pi D2Z B del bar C plus B bar del C bar. Okay, and now what I'm going to do is to consider DB, DC, and similarly bars. We'll do this usual thing. We'll work with the holomorphic sector. Okay, e to the power minus SG, but we will do del by del B at some location, some x mu, with an insertion of B at y mu, e to the power minus SG. Consider this path integral. Okay. Now, this path integral has two terms. Firstly, this is 0 because it's an integral of a total derivative. But this 0 can be broken up into two terms. The first term is just this guy. Okay? So that guy is, of course, by definition, expectation value of delta of x minus y. And then we have the second term. The second term is what? Now we have to get, the tricky thing is always with these anti-commuting objects is the signs. So moving a derivative through an object picks up a minus sign. Okay? So we get minus, but there's another minus sign because we're doing e to the power minus SG. So that's plus. I've got this B of y. Okay? And then I get the derivative of this object. So that's del z bar of C of z. What? At x, exactly. 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 At x. At x. Del z bar at C of x. Z bar. The whole thing is at x. You're right. This is the second coordinate. So basically this is the z bar coordinate of the C insertion.
Yes.
Okay, so let me call this x. This is del z bar on the coordinate x. Okay.
The del z bar of C at the point x.
Exactly. It's the z bar just means it's.
Yes, it's acting on the anti-holomorphic.
Maybe I should have used a z bar for these. Yeah. Okay. You know what I mean, right? Okay. Okay. So what have we got? We've got the equation minus del z bar of, okay, now, okay, B of y, C del x z bar, C of x is equal to delta x minus y. This is x, not square. So now everything's going to be translationally invariant. So let's just call this 0 and z. Okay. So if we look at the object B of 0, C of z, minus del z bar of it.
That will be delta z over here.
What happened to the minus sign? There were two minuses. One minus when I took this through here. This would be one minus because he had an e to the power minus st. This because it put an equal to in between them. This plus this was 0. So this, take to the other side. Okay? No. It's important to get them right because eventually we'll have to check against Polchinski. Yeah.
Oh, the minus is there? I see. Oh,
Yeah. Oh, fine.
And that is delta z.
Z. Now, let's be a little careful here. It's this irritating d2z that we have to be a bit careful about, to get our factors right. Let's call this and I messed up because I should have had a 1 by 2 pi. But I'm going to work with the usual measure. This is d2x. If I want this to be just the usual delta function, I should use the usual measure.
Yeah, Polchinski has the opposite.
He has a very confusing way of thinking. He has, of course he gets it all right. Okay, so this will come with a pi if this is the usual delta function. It's the delta function on the plane. I think his delta function is also a bit different. Yeah. Okay, but if we want the usual delta function, this is what we have. Okay. Now the question is, what?
The other two came basically from the d2z with that 2dx.
Exactly. So now the question is, what is this correlation function? Well, it's something translationally invariant, so it's a function only of z. And del z bar of it is a delta function. Okay? So del z bar of it is a delta function. So we know that it must be 1 over z up to some normalization. So let's see, what is the correct formula? Del z bar of 1 over z, does anyone remember? Is equal to z minus a is equal to pi delta z of z minus a. D to z. Does anyone remember this formula? Polchinski has it. Good, we look it up. Usual delta function. Usual delta function. Usual delta function. I think so too. We could figure it out, but I'll just look at Polchinski. Integrating by parts. Yeah. Somewhere in chapter 2. Yeah. Yeah. Now he reports a formula, but he reports it with his delta function.
Yeah.
And he has a 2 pi.
Half, because we have a major factor as is 2, his delta is a half.
Half. So then, yeah, he has 2 pi. Yeah, he has 2 pi. Okay, fine. Let's go with this. Okay. So if this is correct, then what is this correlation function? This correlation function is now B of 0, C of z must be equal to minus 1 by z. Is this clear? Okay. Now, what about, because he's anti-commuting, this also tells us that C of z, B of 0, is equal to 1 by z. because we get an extra minus sign when we flip them. And since this thing only depends on the difference between coordinates, we all from here we conclude that, you know, if we write, let me say it this way, this is Z1, this is Z2, and this is Z21, which is equal to plus Z12. Okay? So what have we concluded? We've concluded that C of Z1, B of Z2 is equal to 1 over Z12. And B of Z1, C of Z2 is also equal to 1 over Z1. Exactly. You see, had it not been for the minus sign, had they been commuting objects, it would have, this formula is Z of C minus Z of B. So we would have got Z of C minus Z of B. So it would have been Z21, but the extra minus sign turns it into Z12. So it's always 1 over Z of first minus Z of second.
Are these the descendants of same primary or
They're both primaries. We'll see. You see, we've seen that they transform under.
Yeah. Yeah.
We've seen that they transform. They don't transform on Weyl transformation, and they transform on diffeomorphism, which means they're primary fields. Okay, with weights -1 and 2. But we're coming to all that. Hang on. Okay, right now all we've done is compute the 2 pi function. Is this clear? Now the next thing that we want, to do is to define, composite operators. And we're going to define composite operators exactly the same way as we did for the scalars. That is, we subtract conformal normal order every composite operator. So for instance, we want to define the operator BZ, C of BZ1, CZ2. That will be defined, this normal order will be defined as B of Z1, C of Z2 minus expectation value B of Z1, C of Z2. All the machinery that we built last time goes over to this. Okay, so all the formal definitions in terms of the exponential of 2-point function, derivative, and so on just goes over. I won't say it again. Okay, so always when we deal with the composite operators, once again we define them by conformal normal ordering. Why is it convenient? It's convenient because it's a quadratic theory. For quadratic theories, you can always do this. You're guaranteed there will be no divergences in OPs, in correlation functions, that these will be well-defined operators. Then you can take the coincident limit, and there will be no further divergences. Okay, fantastic. So now the next question is, what is the stress tensor of this object? Okay, now what we have to do is to find the stress tensor. These are free theories, okay, and it's easy to find many candidate stress tensors. Our stress tensor has to have the property that comes from varying the metric. I could have had an interesting delta function on the right hand side. Well, you say because this thing is dimension 1. So, and so you could have had a delta of Z. But you know, No, he means a holomorphic delta function. He means just a delta of z. Yeah. No, but there's a yeah. Yeah, the question is what happens to the singularity at the origin? I don't think there's any freedom. Yeah. Yeah. Not at all. I don't think there's freedom because it's like this, right? I mean, see, we know that del squared phi is equal to delta has a unique solution. Now we can break this up into del z bar phi is equal to delta. And this by Gauss theorem,
On this comment that if you put a holomorphic delta there, because this is an anti-holomorphic derivative.
no, that's very dangerous. You might say that same thing for z. It's an anti-holomorphic derivative, so it doesn't see.
So the first, how this del z bar acts on holomorphic delta. Once we figure that out.
Exactly. That's the point. Certainly it won't do anything away from z equals 0. But that's not very interesting because the whole delta function doesn't do anything away from z equals 0, right? It's exactly like this. This thing looks holomorphic, yet we take an anti-holomorphic derivative of, because it has a singularity near z equals 0, it can act.
So we have to figure out
Yeah.
how del z bar acts on this.
And this completely saturates this delta function, the thing that we want. So if it has any action, it would be bad. Now, there is a sense, it's not, holomorphic delta function. See, so as you said, the question you're asking is my answer unique? I found a solution to my differential equation. Is it unique? Okay. So suppose I have another solution to my differential equation. Okay. Then I take the difference between the two. Then it is a holomorphic function that vanishes at infinity and is everywhere genuinely holomorphic. That has to be a constant. And that constant has to be 0. Yeah. Yeah, so that can't be. Yeah.
So here we have seemingly a holomorphic function, or seemingly as a holomorphic derivative and still getting something.
Yes.
Is that because at the origin z
The
equals
singular.
bar?
No, because there's a singularity. Meaning, z is 1 over z is not quite holomorphic. It's holomorphic everywhere away from z equals 0. Like singular z equals 0.
So the definition of not depending on z bar
Is
is not.
not so well. Yeah. This business about this you can understand from Cauchy's theorem. But let's get into all that later. There's a nice way of using Cauchy's theorem to see that Cauchy's theorem is basically equivalent to this statement. You know, it's basically that at a pole, Cauchy's theorem picks up things at a pole. It's behaving very much like a delta function. It's that kind of thing. But okay. Fine. So let's keep going. So where were we? We wanted to find the stress tensor. So now what I'm going to do is to write down a bunch of candidate stress tensors. Okay? See, what have we seen? The equations of motion make C holomorphic. The equations of motion also make B holomorphic, away from insertions of other fields. Right? Because the equation, this was this equation that, I mean, just look at the equation of motion here. Del z bar of C is 0, or integrated by parts, del z bar of B is 0. Within a path integral, classical equations of motion always apply, apart from insertion points. So B and C are both holomorphic fields. We're looking for, let's say, the holomorphic part of the stress tensor. So we will make it out of B's and C's. Okay? And we're looking for something that is going to have dimension 2. We know that this quantity here has to have dimension 2. This, I mean, we want it to have dimension 2. This quantity has dimension -1. So we will make it out of a B, a C, and a derivative.
Just one question I was probably so in the path integral, we have written dB and dC, which sort of implies that they are both independent fields. But they are not completely independent, because B and C are sort of the conjugate momenta to each other.
Well, just in terms of what you're integrating over, yeah, it's true that they're conjugate momenta to each other if you think of it classically.
Yeah.
Or in language of canonical quantization.
Yeah.
But this is like a phase-space path integral.
Okay, okay.
In the path integral, they're just completely independent. Okay? They're just things you integrate on. Okay, great. So where were we? So what we wanted to do was to understand the stress tensor. So one way of doing it, and I'll just leave that as an exercise. If you guys are actually doing exercises, please note this down as well. Okay? I know I keep, okay. One way of computing the stress tensor in this particular case is very simple. That is, just take the original action which we had as a function of the metric and vary it with respect to the metric. Okay? That will give you the stress tensor. I'm going to follow a way of guessing the answer, because this way of thinking will give us access to a whole range of conformal field theories, and we will need them at different values of parameters at different points. You see what I mean? No. Okay? So this, the straightforward way, which is totally algorithmic, I'm leaving as an exercise, and I'm now going to help you try to guess. So what we're going to do is to write down a candidate stress tensor, and we'll follow Polchinski's notation. If I can find my spectacles. And then we'll see how it goes. So let's take T of Z is equal to normal ordered dBc minus lambda normal ordered, or del of normal ordered, doesn't matter, normal ordered BC. Let's take this as a guess. You know, what we need to do is to take something which has a derivative on either C and B, or derivative on either B or C. This is one way of, he's chosen one coefficient which will turn out to be the coefficient that is conveniently normalized, that is appropriately normalized. And there's this guess thing lambda, which we'll work with. Okay. So now what I'm going to do is for this stress tensor, and using this operator product expansion that we've just derived, I'm going to work out the Virasoro algebra.
So normally the way we define stress tensor in terms of you vary the metric with respect to the, or vary the x with respect to the metric. But now we're starting the other way. We're saying let's guess the stress tensor.
Yes.
What does it have to satisfy first? How would we know if our guess is right?
What we will need is that under the stress tensor, C is dimension 1, minus 1, and B is dimension minus 2.
Those are the only things we have to test?
And firstly, it has to be a stress tensor that obeys the Virasoro algebra. Okay? And secondly, under the stress tensor, C has to have dimension minus 1, B has to have dimension 2. As I said, for this particular case, you don't need to do any guesswork. We know how the thing couples to the metric, we just derive it. Okay? But through our study of string theory, we will find, as I'll just tell you, we will find that this stress tensor works with lambda equals 2. But through our study of string theory, we'll encounter the same conformal field theory at different values of lambda. Okay? For this reason, I want to introduce you to this class of conformal field theories once and for all.
So those are only, our checks are basically Virasoro algebra and make sure that the dimension of the operators that we know from other constraints.
Other constraints,
Right.
and the other constraints is how they couple to the metric.
Okay.
Okay,
So we'll be going
so
back to
yes,
that.
so the way to get it systematically would just go through the metric. I'll leave that as an exercise for you. What? Same action, same action. It's just different couplings to curvatures. You see, this is an improvement term in this stress tensor. Some total derivative that will not contribute to charges. Let me say again. This is something you're probably familiar with, but let me say again. You know, suppose I give you an action in flat space, and I ask you what is the stress tensor. Well, you could take that action and covariantize it, and then differentiate it with respect to the metric. That'll give you a stress tensor. But suppose I took that action, and I added a curvature coupling to it. R times something. Now I differentiate that. I'll get some new contribution. Both these actions are the same in flat space. They're different generalizations away from the flat manifold. If you know the action coupled to an arbitrary metric, you know the stress tensor. But there is, if you just know the action in flat space, there's ambiguity in how to couple it to an arbitrary curved metric, because you can add curvature type coupling. Okay? So it's possible for the same action in flat space to be associated with different stress tensors. Okay? And that's what's going to go, that's what's going on. So if you know how it is coupled to the metric, like we do in our case, there's no ambiguity. You can just derive it. Okay? But we're going to encounter, for instance, I don't know, those of you who are familiar with this, if I call this field psi bar and this field psi, then this will remind you of the Dirac action. And the Dirac action has this stress tensor without this term. Or maybe lambda equals, I mean, it has a different stress tensor. It couples to the metric in a different way. Okay? So that's an example. It's an example we will use because when we work with the superstring, we'll need the Dirac action. Okay? So there are many different ways of taking this thing and uplifting it to a... Yes. Another way of saying it is that we're, you know, in 2 dimension, the effective spin of each field is different here. This field is spin 1. In the Dirac action, the spin of the field is half. So the coupling of this metric to the spin connection of the fields to the spin connection is different. And that will show up in the stress tensor, because the stress tensor will tell you how to rotate. Okay? But you don't see all that just from the flat space action. You don't need a spin connection. Okay? Fine. So let's just take this object and do some algebra with it. Okay. So what I want to do is to compute T lambda of Z, T lambda, so I won't write lambda, T of 0, and I want to expand it in OP. Of course, all I'm going to do is to use Wick's theorem as usual. Okay? So first, let me take the most singular term. This is the term in which I contract this del B here with the this B here with the B of the other guy. Okay? So let's do it. It's a pain, but we'll just do it. Okay. So we've got, and let's call this Z1 and Z2 so that it facilitates taking derivatives. Okay? So there are 4 kinds of terms. Okay? There's this term with itself. That term is how? This del B will have to contract with, what we want is the contraction del B of Z1, C of Z1, del B of Z2, C of Z2. We want this Wick contraction. Now I've written it like this because we have to keep track of minus signs. So I take this through here to contract with this guy. That's 2 minus signs. And then I contract this guy with this guy. Okay? So this Wick contraction, this contraction gives us del Z1 of Z12 that's this term, and del Z2 of Z12 that's this term. And 2 minus signs, so no further minus. Okay, so del Z1 of Z12 is minus 1 by Z12 square, and del Z2 of Z12 is minus del Z1 of del Z12, which is a plus. So plus 1 by Z12 to the 4. Okay? Minus. Thank you. Minus Z12 to the 4. Thank you. Excellent. So that was the first term. Then there was the term which was this guy of the first with this guy of the second. Okay? This guy of the second is, so we just keep track of this. So this is the first term. Now we're doing the second term. This guy of the second will get minus lambda, and this is derivative of Z2. So Z del Z2. And then we do the contraction ignoring all of these. Okay? So now we have to contract del BC with BC. And then take the Z2 derivative. Okay? Del B goes through, so 2 minus signs. And then we get del Z1 of, so we get minus lambda del Z2 of, this one gives del Z1 of Z12. And then this whole thing gives 1 by Z12. Okay? So this bracket is minus lambda del Z2 of, now this will give us a minus sign, so plus lambda del Z2 of 1 by Z12 cube. Right? The minus sign here, cancel the minus sign there. And so that is minus 3 minus 3 lambda. Plus, yes, plus because the Z2. So plus 3 lambda by Z12 to the power 4. All good? So that's number 2. Now let's do the other guy. Okay, the other guy of course will be very similar. Very similar, it'll just change this to 6. But let's just convince ourselves that that's right. Okay, so the other guy is what? It's minus lambda del z1 bc with del bc, right? Take the b through here. So it's minus lambda del z1. We've taken the b through there, so that's 1 by z1 2. And then we take this, so that's del z2 of 1 by z1 2.
Yeah.
That's c del b.
Yes.
Okay. Now this guy is with a plus. So that's minus lambda del z1 1 by z1 2 cube. And this has a minus, so it's minus 3. So that just makes this 6. All good? So 2 plus 3 has a 6. And finally, this guy with this guy. Okay, so that's 2 factors of minus 2 factors of lambda, and there's lambda square. Del z1 del z2 of 1 by z12 square. Please check. Okay, now we act with a del z1. That gives a minus. Del z2 does not give the minus. So it's overall a minus. The first guy gives a 2, the next guy gives a 3. Minus 6 lambda square. And so the most singular term we have concluded is 1 by z12 to the power 4, and we're supposed to write half. Okay, so minus 2 minus 12 lambda, no, plus 12 lambda, plus 12 lambda, minus 12 lambda. Okay. The remaining terms in the Virasoro algebra, checking the 1 by z12 squared and 1 by z12, that works out. I'm leaving that as an exercise for you guys. Okay, similar, very similar. Less work than this one because you just have to do one contraction. Okay? But now we have, so this claim, when you do it, you find that the Virasoro algebra is obeyed, so T lambda Z T lambda of 0 goes like half C by Z12 squared plus 2T of 0
To the
4
4.
Z12 squared plus del T by Z12 T lambda, where C is given by this object. We checked only the first term, but the other terms I'm claiming work out. Okay.
Why first term is minus?
Minus 1, and then we had a half. Half in our definition of the Virasoro algebra, the coefficient of 1 by Z12 to the 4 is C by 2.
But then we had 4. That was 4 down. Sorry. That was power. That was power.
Yes.
Sorry.
Okay. Excellent. Now, the next thing I'm going to do, because it's less algebra, I'll just do it in class. I'm sorry, this is a boring class, right? But okay. The next thing, because it's less algebra, I'll do it in class. I'll compute the OP of T with Z, with C and T with B. That's quite easy. Okay, so let's do it. So del BC minus lambda del of BC. I'm not writing the normal orders. Understood? All at Z with, let's say, C at 0. Okay. Now this is sort of easy. Where do we get the singular pieces from? We get the singular. Exactly. So let's compute this del B with C. That term first there's a minus because you take this through.
Yes.
Then you get del Z1, 1 by Z12
Times C of Z1.
times C of Z1, exactly. Okay. Then we get the contribution from here, which is minus lambda del Z1. Then we get a minus plus we get C of Z1 and Z12. Okay? Now we open this out. So this is plus 1 by Z12 squared C of Z1, okay, plus lambda times, now there are two terms, this could act here or this could act here. Okay, so first let it
Minus lambda is 1 over V1.
yeah, it's a bit silly. Anyway, let me do it. Let me do it. Plus, so first let it act here. So that's minus lambda C of Z1 over Z12 square. Okay, plus lambda del Z1 C of Z1 by Z12. Now we are supposed to expand this around with all operators evaluated at Z2. So we get C of Z2, the leading term, by Z12 squared into 1 minus lambda. But both of these we have to expand, Taylor expand. Okay, so we get plus right. So we get plus 1 minus lambda times del C over Z12 from the Taylor expansion of here. And then plus lambda del C. Now everything is at Z2 over Z12. And so we get C of Z2 over Z12 squared plus del C of Z2 over Z12 plus. Okay? Sorry, one. It's there, it's there. This is precisely the form of the OP of the stress tensor with the primary operator. If the primary operator has weight, 1 minus lambda. Okay. And lastly, we'll do the guy with B.
So at this point, just knowing how C is supposed to measure, we can already say all that, right?
Yes.
And this will go back and tell us what the informal charges from the
Central charges. Yeah, so in fact we get lambda equals 2 as you see, since we need C to be minus 1. But let's also check B, just so that we're sure we've got all algebra right. Okay, so now we're going to do the same thing. I'm being very unsystematic here, but you don't mind. Okay, we're going to do the same thing, but with B. Okay. So then the first term is del B at Z1 over Z12. okay, plus minus lambda del z1 b of z2, no, z1 divided by z1 2. Okay, so one term is this guy hitting this, so that's lambda b of z1 divided by z12, okay, minus lambda del z1 b of z1,
So by z1 square, the first one.
thank you, minus this by z12, and then plus del b of z1 by z12. Now you see that the Taylor expansion of this cancels this. You know, the term which is 1 by z12. So we get lambda b of z2 over z12 square plus del b of z2 over z12. And precisely the form of a primary operator with weight lambda. So now it looks good. If we set lambda equals 2, then B has weight 2, C has weight minus 1. And now let's check what the central charge turns out to be. Let's check minus 2 plus 24 minus 48 is equal to minus 26. Okay? Now, what is the significance of this minus 26? You remember 4 or 5 lectures ago, we looked at how the partition function of a conformal field theory scaled with the change in the Weil factor, changed with the scale of, with the Weil factor of the metric on which it's evaluated. And we got some detailed answer, C by some number times phi, del phi, this Liouville action. And in particular, the partition function was non-invariant under Weil transformation. How does this affect us here? You remember we've gauge fixed, and we've gauge fixed to some metric G0. Now, if our answer depends on which metric G0 we've chosen, the answer just doesn't make sense. But we know how the answer for a conformal field theory depends on the metric that you choose to view the conformal field theory on. C R 1 by del squared R. Okay? It cannot depend. And therefore C must vanish. That's the only way. Is this clear? Let me say it again. It's simple, simple. You see, we derived for a conformal field theory that Z as a function of G.
Yes.
You start with any G0 and you perform a diffeomorphism plus Weil transformation.
Yeah.
Okay? Suppose Z e to the power, okay, let me just write it for Z G e to the power 2 phi. Eta, okay. Z of G with any diffeomorphism plus Weil transformation. Okay, related to Z of G0. Okay, by the integral e exponential of C by I can't remember 12 R 1 by del squared R.
Very important that this action usually action is not clear about the actual action on the space.
Yeah, it was just completely determined by the central charge.
Very important.
That's a very important thing. Or in particular, if we restrict ourselves to just Weil transformations, we do delta times e to the power 2 phi. This thing was exponential of C by 12 del phi the whole thing square. Hmm.
So
Hmm.
radial mathematically particular theory.
Well, you know, the coefficient of r squared, you give some names to.
Give some names, but it depends on the particular field only through the coefficient.
What does it mean?
Like in this two-dimensional case, this how does partition function change under this field? Care about the particular theory only through the number c.
Only through the number c, which was the number that appeared in trace t is equal to c times r.
Yes, it cares about the theory only through this coefficient.
Yes.
And because of that, this particular ghost theory, which is a totally different theory and contradicts theory,
Yes.
they can cancel each other. These factors can cancel each other.
Yes.
If it cares, because c's are opposite,
Yes.
it will care about more.
Yes.
In higher dimension, it will care about the theory only through that kind of coefficient.
So once again, you know, there will be three numbers, let's say. That's in 4 dimensions.
So there will be those dependence only through the numbers.
Those numbers are just numbers. Now, it could be that as you change the theory, the number changes.
Yes, that's what I'm saying. The numbers care about the theory.
Yes.
So
Yeah. It's just numbers times structures.
So therefore, in higher dimension also these kind of things can happen. Some two totally different theories with numbers cancelling each other.
Could be genuinely wild invariant.
Genuinely.
Yes. Yes. The structure of this, just the anomaly structure of this, is fixed by some numbers.
Some numbers, it's only these numbers.
It's a, yes.
These are the
Yeah. Okay. Now, what was the logic? The logic was that in our string theory path integral, we had a matter and a ghost action that had a metric in it. The metric was g naught of tau, let's say. For every equivalence class, at random we picked one g naught. Now, if we have got the formula correct, if we've got a formula that makes sense, the answer cannot depend on which g naught in that equivalence class of metrics we picked. But that is exactly the question, since the answer that we're getting is a path integral of a conformal field theory. The question of whether it depends on that equivalence class or not is precisely the question of how the partition function of a conformal field theory, scales as changes as you change the base metric g naught. That's precisely the question we've answered in conformal field.
Also in a particular equivalence class, I can do y transformations and I can do diffeomorphisms, but this factor seems to only care about the y transformation.
Because you always keep diffeomorphisms and exact symmetry of your theory. Always regulate theories to keep diffeomorphisms. You see, diffeomorphisms are easy to keep straight, while are less easy, because while transformations change scale. So any cutoff is in tension with while transformations. Because the while transformation changes, the cutoff gives a scale and the while transformation changes it. So it's harder to maintain while invariance. Okay?
So does this, let's say this scale, does this make like renormalization?
Renormalization of what? If C is 0, you're saying?
Well, I'm saying if you can just change scale with no cost. This seems like a
Well, you know, we were in a conformal field here. So on flat space, you could always change scale for no cost. What's interesting here is that does more than work in flat space. It becomes a genuinely position-dependent renormalization invariant theory. You know, in renormalization, what we do is change a cutoff everywhere uniformly in space. Here you can do more. Yeah. In a conformal field theory, you could always do more, but there was a price to pay. You wouldn't get back the same action. Yes, yes. Okay, but even there, in an ordinary conformal field theory, if you changed the cutoff in a position-dependent way, you did a while transformation, self-equivalent thing, you almost got back the same answer, but up to a price, which is this price.
So the logic that we said over there was that you take some theory and then go away from it by some wild transformation. You get a theory that looks different.
you know how to map one to the other. However, in this theory, in string theory, we're interested in the value of the partition function. You know, we're not interested in some normalized thing. We want a number for the string scattering amplitude.
Right, and I know how to relate them. That's okay. So you describe it one way. I know how to get you the same number as the other in the seemingly modified.
But one of them is the right number. One of them will be measured at LHC. Which one? I agree that if you...
I mean, that's just to use an analogy, that's like saying, right, if you get the LHC book, they tell you to do an MS bar. Right. These are conventions.
No, they're not. These are scattering amplitudes.
No, but this, you can relate the scattering amplitudes from one theory to the other. And if this equality is equality, then I should be getting the same number on both sides.
Wait. It's for the partition function you get that exponential times the new partition function. It's true that if you know the partition function in any one choice of Weil frame, you can figure it out in any other because it's simply related. So if you had a physical reason to pick out one Weil frame as special, you could say that is the one that we will measure at LHC. And then if you do the calculation in any other, that may be convenient for you, and then I can translate to this one. But we do not have that reason. There was no distinguished metric. Okay? So in a situation where this partition function is itself a measurable quantity, it should turn out to be as a number independent of that metric. It is not good enough for us that there's equivalent information.
And it's not like, again, it's not like we're normalizing it so this output.
Yes. Okay? So for this answer, it's basically, we're computing a measurable quantity, what we will claim is a measurable quantity. It's like, these gauges that people use in QED, this thing that interpolates between Feynman gauge and Landau gauge. I think they put an alpha behind. It's like getting an answer that depends on alpha. Even if it depends in some not too complicated way, if you're computing a scattering amplitude, cannot depend on alpha. It's very close to that. It's just a gauge fixing. Quantity is supposed to be some physical quantity. We compute it in some gauge, you cannot get a different answer from that. Okay? So, we are forced, therefore, to go through this whole procedure. This whole procedure here only really makes sense if the matter conformal field theory has central charge 26.
So it also, and this might be
Go on.
that integral over there, it might be something like the Gauss domain kind of theorem where that ends up being and then you treat that some sort of
No, this will in general not be an integer.
I mean, even the one with the R.
No, not even that, because that's 1 by del square.
This is not going to be.
It's not going to be. It's something that you can continuously interpolate between.
You can.
This phi can be made small, for instance, and won't cancel. It's positive definite.
I'm sorry, I missed the comment about why it's 26.
Why it's 26? Because the ghost central charge was 26. The full path integral of string theory has the matter sector and the ghost sector. Right? This depends on the full central charge. So if the full central charge evaluates to 0, then this is independent of, then our whole path integral was gauge invariant, independent of how we gauge fixed. Okay, so it had better be that the matter sector has central charge 26.
Yeah.
But we remember that the central charge of one free boson was 1.
Yeah.
So how do we get from central charge 26? Take 26 free bosons. Okay. Now there's already something a little non-trivial here that turned out to be an integer. Right? Had this central charge been square root 2, there's nothing you could have done. I mean, not easily. Okay, or even minus. Firstly, it's a negative number. Secondly, it's an integer. So it leaves some room to wiggle around. But the thing that's really interesting is that it's not the first time we've seen 26. Yeah. You remember that when we were right at the beginning of the course, when we started looking at the spectrum, we found that we wouldn't get Lorentz invariance unless C was 26. Okay, now These two things seem like different things, but of course they're related. Why are they related? Right, why are they related? You see, what's going on here is that this theory is not truly while invariant unless C is equal to 26. Now, by using all our symmetry, if all our symmetries were symmetries, then we can use any choice of gauge fixing and we get the same answer. If all our symmetries were symmetries, then we could use Lightcone gauge. Lightcone gauge appears to break Lorentz invariance, but it must give us a Lorentz invariant answer because it's equivalent to using covariant gauge, which is obviously Lorentz invariant. Okay, but if gauge transformations are not invariants, then how you fix gauge matters. Just like we've seen here, right? The choice of G0 could matter. So choosing Lightcone gauge could matter. And then if how you choose gauge matters, you choose a gauge that breaks a symmetry, chances are the answers won't present that symmetry. Right? So it's only when you've got a genuine gauge symmetry that you can do things at will. So this while transformation, which was while invariance, which was key in the logic of the whole procedure. Because that while factor, remember, in the Nambu action wasn't even there. We introduced it by hand. So it better be an invariance of the theory. Do you remember the relationship between Polyakov and Nambu-Goto was one of the equivalence classes? A space-time metric. But there was no world sheet metric. Okay? And so what we're saying is that if C is not 26, for the matter part is not 26, this while invariance is the genuine symmetry of the theory. Okay, it's broken in a very subtle way, but it's broken. Okay? Then different gauges will give you different answers. And so if you do a Lightcone gauge, you'll find that it's not Lorentz invariant. You do it here, you find it doesn't vary in G. Okay? So this is our first victory. We've done things sort of more sophisticatedly than the first few lectures, as I'm sure you'll agree, and we got the same answer. That's sort of nice. Okay. So we conclude once again that D must be equal to 26. Excellent. Now let us go on. Okay. There are three, okay, we're running out of time. There are 3 or 4 things I wanted to say about the BC CFT. The BC CFT, I'll give you a few exercises, but we'll say a few things and then I'll give you a few exercises. What? BCCFT. Everyone calls it BCCFT. The first thing I wanted to do here was work out the state operator map. Okay? So let's take the state corresponding to identity, the operator identity. Okay? Firstly, we should do some mode expansions. So what we're going to do is to take B of Z, it's of dimension 2, and so we'll expand it as Bn by Z to the power n plus 2, as usual. And we will take C of Z, which is of dimension minus 1, and so expand it as Cn Z to the power n minus 1. This is the standard story, so that these become the usual modes on the cylinder, as we discussed before. Okay? Yes.
We don't end up with anti-commuters, right? Instead of
Good question. So now Upmanyu is asking. This is a good question. Let's work that out. Upmanyu is asking, what is the difference between having commuting and non-commuting guys? What does that do to your, if I'm understanding you right, to the contour manipulations?
right.
Let's figure that out. So let's do that in an example. Okay, what we want to do is to do the following. Okay. I want to see what I can say about the algebras of B's and C's. Just like we figured out the algebras of LNs using the OPE of T's. I want to see if I can figure out the algebra of B's and C's using the OPEs of B with C. Okay? So let's see. So now what I'm going to do is the following. First, let's write down formulas for Bn and Cn. Bn, as usual, is 1 by 2 pi I integral z to the power n plus 1 B of z. Cauchy's theorem, that's still true. Cn is 1 by 2 pi I integral dz. Z to the power n minus 2 C of z. Okay? Now I want to say, now I'm claiming that the thing that we can easily figure out from OPs is not Bn Cm minus Cn Bn, not the commutator but the anti-commutator. Let's check that. Okay. So suppose I had, it's just very simple. The main thing is this. See, once, yes. It's because in a commuting path integral, the guy that's before or after is just the one that is later time or earlier time. In an anti-commuting path integral, the guy that's before or after is the one that's later time or earlier time, but you have to move them physically to the left or the right. Let me say what I'm saying. See, suppose we've got an anti-commuting path integral. We've got an anti-commuting path integral, so we've got an e to the power minus action, and we've got some operator inserted, some operators inserted. Okay? And we have some O of T1, O of T2, O of Tn. Okay? Written in, so suppose maybe Tn minus 1, T1. Written in this order, if these operators don't, if these things are numbers in the path integral that do not commute with each other. Written in this order, this thing maps to, okay, and we're doing T1 is less than T2 is less than T3, this is Tn. Okay, so suppose we have a path integral like this. We write it in this order, and remember that's different from this with a minus sign. Okay, that maps to OTN, OTN minus 1, OT1. Okay, now inside this path integral, I could switch the position of this and this. That just means minus of this. The positions here are very serious. It's positions of operators in a Hilbert space. It's the order in which you take a trace, for instance, order in which you take an expectation. The positions here care only about minus signs. It's like AB or BA. These numbers inside, these numbers are either commuting or anti-commuting. Just inside an integral. Is this clear? Okay. So suppose you've got some path integral and you've got some insertions, you're supposed to flip the order so that the latest guy, the guy with the latest guy, appears to the left inside the path integral, and then you're allowed to interpret it in Hilbert space terms. That's the rule. We don't think about this for bosons because that flipping the order makes no difference. But when you have fermions, there's an ambiguity, and this is how you're supposed to fix that ambiguity. Okay? So now it's very clear. Suppose I take this guy. What does it mean? Okay, so suppose I take this. So I take this, which means in formulas, it means, so say B was this color and C was this color. Suppose by this I mean integral dz1 by 2 pi I B of z1 C of z then dz2 by 2 pi I C of z2 times z1 to the power n1 plus 1 and z2 to the power n2 minus 2. Suppose that's what this formula means. Okay, and this formula means what this means is, I mean, I'm going to write it in a way that it reflects the rule. So the guy that's outside is always to the left. Suppose that's what it means. This is, so, you know, the same things, but dz1 by 2 pi I, dz2 by 2 pi I, C of z2 by z2 to the power n2 minus 2, and B of z1 by z1 to the power n1 plus, sorry, z to the power, you know. Plus 1 or whatever it was. Okay. Then we previously got, you see, we previously got a relationship for this minus this. That's what was converted into contour integral. But because here there is a trivial change, namely with the CB, we'll get all the same algebra, but for this plus this. Do you understand? Because what we'll do now is take this object and rewrite it with the B to the left and C to the right. So let me say that. Let me say that to be really clear. So let's say this is C1. Exactly. So I'll say it as clearly as I can. Say this is C2. Now there is C2 tilde, which is equal to minus C2, which is the same contour, but these two flipped. Okay? Now, all our analytic arguments just were about correlation functions.
In a sense, we can actually think of this sort of going around each other as like sort of the origin of how to figure out your statistics, and then you just work it out.
You work it out, but it's a very simple working it out. Right. So see, because once you've got BC up and BC down allow you to close the contour. Okay? So C1 minus C2 tilde is related to the OP. But it's not C2 minus C2 tilde. It's not C2 tilde that has the simple Hilbert space interpretation. It's C2 tilde. It's not minus C2 tilde. It's not C2 tilde, it's C2. Yeah. Okay? So when you say C1 minus C2 tilde, okay, that is in Hilbert space Q1 Q2 plus Q2 Q1. Is this clear? It's a very simple point. Okay? So all our contour arguments go through, except everything goes through without change, except that the formula is that the commutator between any two operators is given, the anti-commutator between two operators given by the residue of the singular terms. Okay? So now let's compute anti-commutator of CMBM. Oh, very quick, I'll try to finish fast. So anti-commutator of CNBM, all we have to do is to take these currents. We have to take residue of z to the power n minus 2 times w to the power m plus 1, and then we have to take the OP, which was z minus 1 by z. Let's call this z1 and z2, z1 and z2, divided by z1 2. Right? But now, because this is such a low singularity, we just set z1 equal to z2. So we just get z2 to the power m plus n minus 1. Then we have to do the path integral. And that's 0 unless m plus n is 0. And so we get Cn Bm anti-commutator is equal to delta m plus n 0. The rule, remember, was that the residue gives you the current that you have to integrate over. In this case, the current was identity times something which gave you a charge, which was 0 unless it's kicked. Is this clear? Is this clear? Was it too fast? Okay. Unless somebody speaks up, I'm going to assume it's clear to everyone. Okay. So we've seen that these modes, these BNs, CNs, are the modes of fermionic harmonic oscillators with, destruction and creation of one pairing with the other. Okay? Now L0, as always, N tells you the energy under L0. So negative N's raise energy, positive N's lower energy. So the vacuum of the theory, okay, the vacuum of the theory is the theory, is the state which is killed by all positive N's and not killed by all negative N's. However, that leaves a particular N that we have said nothing about, namely N equals 0. Okay? So let's look at N equals 0. What is the algebra of the 0 modes? The algebra of the 0 modes is this: C0, B0 is equal to 1. Okay? C0, B0 is equal to 1. This is the algebra of sigma plus and sigma minus. It's the algebra of, this algebra is very easily implemented as follows. Consider the mode annihilated by B0 on state psi. Let's call that down. So 1D Clifford algebra. It's two-state system. Okay, B0 annihilates down. Then what can we say about C0? C0 and down, whatever it is, we'll call it up. Now, C0 on up is C0 squared on down, but C0 squares to 0 by that algebra. The only non-zero ones here are C's and B's. Oh, I forgot to tell you, but
Yeah, I mean,
that's obvious. Because there's no non-trivial OP, no singular part of the OP between. We'll get the same thing. That's Cn, Cm is 0. Anti-commutator is 0. In particular, Cn is 0. So Cn squares to 0. And similarly with the BMs. Okay? And so this thing is C0 squared on, so this is equal to 0. Okay? And what about B0 on up? Well, B0 on up is equal to B0 on, but up was, yeah, exactly, C0 down. But then we use the algebra. So that's equal up, sorry, that's equal to B's, yeah, this was down. Sorry. This down plus 0 because B0 annihilates down. Okay. And so the zero mode part of the algebra has this two state. The representation of the zero modes is this two states sector.
And the least irreducible representation. I mean, obviously.
Yeah, the representation is two state sector given by this algebra. B0 annihilates down, B0 and up makes down, C0 annihilates up, C0 and up makes down makes up. It's very simple representation. It's same as sigma plus sigma. Okay? So what we have is now a twofold degenerate vacuum. So the question of what is the vacuum of the theory makes no sense. There's an upstate and a downstate. And then on top of this vacuum you can build with the oscillators. So what's the whole Hilbert space? It's given by C, the occupation number of the Cn oscillators for n is equal to 1 to infinity. These occupation numbers can either be 1 or 0 because Cn squared is 0. Okay? The C minus n squared is 0. The occupation numbers of the B oscillators, n is equal to minus infinity, and this the guy in the two-state sector.
So it's just an NF system, but with an oscillator sort of energy stack on top of it.
Yeah, each of these is a fermionic oscillator. So just like for the bosons, we had a bosonic oscillator at each end. Here we have two fermionic oscillators at each end, except it's 0 where we have one fermionic oscillator, which is this. Is this clear? That's what this BC system is from a Hilbert space point of view. Okay, last thing I'll do today, and I'll let you guys go, is the state operator map. So now that we've got all this machinery set up, we can ask what is the state proportion corresponding to identity. Okay? In order to figure that out, we'll use the same tricks as we used for the free bosons. So we'll just take all these charges and act on it, see what we get, and from that figure out what the state is. Okay. So let's take the state corresponding to this and let's act with Cn. Cn on I is by definition because identity is nothing. This thing is now 0 if n is greater than equal to 2. Okay? Not necessarily 0 if n is 1 or 0. Why do I expect this for? Okay, I'm just working it out. I expected this to happen for B somehow, but let's. Oh yeah, no, it's fine. It's fine. It's C. Okay, good. Okay, and now let's do the same thing with B's. Okay, it's 1 by 2 pi. So Bm on identity is equal to, forget the 1 by 2 pi, integral z to the power n plus 1, m plus 1 dz, and so it's equal to 0 for m greater than or equal to minus 1. Now with this data on hand, can somebody tell me
what is this arrow?
which arrow?
Actual identity has some, is it some sort of a singular or something? It's up down. What is this up down?
What is this up
You
down?
can figure out this way. I am sure.
What?
But you are figuring out this way. Right now you will figure out what is this inverse state.
I will figure out. Yes.
Yeah. But this up down is some sort of a charge. Can you understand?
This up down differs by ghost number.
Ghost number. So we want something to be 0 for the identity.
Oh.
Some
Yeah.
that will make some symmetry analysis. Tell us that what combination you want.
Yeah.
What is ghost number 1 in your combination?
It's always tricky because the vacuum carries ghost number. You know, let's say for operators, C has ghost number 1, B has ghost number minus 1. Okay? But the question of what the ghost numbers of states are is a more tricky question. So clearly identity will map to an operator with ghost number. We will analyze this. We will analyze the ghost numbers of states. Okay, it comes from the anomalous transformation of the ghost. We will analyze this. Okay, but let me just get the answer. Okay, so now somebody must tell me the answer. The question is, I've got the state. All B's with m greater than or equal to minus 1 annihilated, and all C's with n greater than or equal to 2 annihilated. So let's say that this is our notation for the vacuum. There are two vacua. It's a notation for the twofold degenerate vacuum. In terms of this,
So obviously the down is annihilated.
huh?
The down is annihilated by the B.
Good. So is your proposal that it's down? One proposal might be that identity is equal to down. That doesn't work because
Yeah, but I'm
good, but it's a
Find out the dimension 0 quantity. These C0s are dimension.
well. First, let's just do it algebraically. It's just look at it. Yeah,
Down is what?
down is good, but what? You see, the vacuum had either of the vacua had the property that B minus 1 created a state on top of it.
so some antisymmetrized combination of down and up.
No. B minus 1 annihilates the state. So this must be B minus 1 on this. Now let's check. If it is really B minus 1 on it, then C1 will not annihilate the state. But C only annihilates it for n greater than or equal to 2. So that fits. So you see that identity operator does not correspond to the lowest energy state. It's not one of the two vacua. It's one of the excited states built on top of one of the two. In this very funny theory. Okay? It's very funny. You don't like it. Let's keep going. 0.
Any coordinate.
Any
We
coordinate.
don't want to do that.
Yes. Yes, we will see how that works. Okay, that requires more complicated analysis, so we won't do that now. Okay. Now let us look at the operator corresponding, the state corresponding to the operator C. That's a nice primary. It corresponds to some state. Let's figure out what that is. Okay. So now, what do we get when we act with Cn? Z to the power n minus 2, C of Z, C of 0. We have to do this. Now, is this guaranteed to be 0? Greater than or equal to 2, then it's guaranteed, but that's not, you can say a little more.
So what is our P in this one?
You see, C of Z with C of 0, because they're anti-commuting, always starts with Z. Because the constant part is C0 square, which is 0. So this guy goes like Z. So this whole thing scale is like Z to the power n minus 1. So n greater than or equal to 1 gives 0.
Yeah.
Okay? So Cn on C equals 0 for n greater than or equal to 1. Okay? Now let's do B. When we do B, we have Z to the power n minus 1, so Bn on C, Z to the power n plus 1, but then we need the OP. The OP had 1 over Z. So we get Z to the n. Okay, so this is equal to 0 for n greater than or equal to 0. Now tell me what state it is. Yeah, exactly. She is down.
Your identity is B minus 1 is down.
But just look at it. You see, down is annihilated by B0 and all subsequent B's because it's a vacuum. And it's annihilated by all C's except C0. I mean by C's with negative ends. But not by C0. That fits. Okay. So the state corresponding to down is C. Okay. Can somebody guess what is the state corresponding to up? No. Now you see, B carries dimension 2.
Oh.
So whatever the state corresponding to B is, you could have guessed that the state corresponding to C would be a vacuum once you know that identity is an energy 1 state. Because C is dimension minus 1. So it will lower the energy by 1. So it will go to a vacuum. Which vacuum you may have had to worry about. Okay? However, B raises energy by 2. So the operator corresponding to B will be some 3 excitation state. Third excitation level 3. 2 above the vacuum, 2 above identity. Okay? So we want to, C did this lowering. Anything else you can think of that will do a lowering?
Some BC denominator.
What is the operator corresponding to the state up? What? The derivative of B is even worse. It's dimension 3.
It's some combination of BC.
B, C. Once you have a B, you're in pretty bad shape because it's dimension 2. It's a big one. And that's you're on the right track. C0 times. Okay, just because it's so late, is C del C. C has dimension -1, del C has dimension 0. So this is an operator which corresponds to, it's quite strange system. You can check all these, okay? And so as an exercise, find the state corresponding to B. Exercise, check this, find the state corresponding to B. Okay, fine. So we've had our first brush with the BC CFT. The next thing that we need to understand about it is about Gauss number. Okay, we will do that next tomorrow. And then we will use our knowledge of this to construct the BRST. The BRST current for string theory. And then really understand that string scattering amplitude formula in its gut.